Hello, my dear fellow engineers. I am Mohammed Ismail Hussain, representing Ascending Consulting Engineers. And today we will delve into an important yet often misunderstood topic, which is uplift capacity of shallow foundations. In this video, we will be discussing about foundations embedded into the sand or laid into the sand. For foundations laid in clay soil, we will make another part of the video. This video is sponsored by Ascending Consulting Engineers. Ascending Consulting Engineers is a recently launched structural engineering firm in Bangladesh. The firm mainly specializes in structural design, detailed engineering assessment, seismic design, bridges, retaining walls, foundation engineering, and its strengths and silos for API 650 and other coarse pavement design using HTOR, PCA methods, and facade systems. Okay, let's get back into the main video. So at first, let's start with some basic questions. The first question is, how do we already measure the uplift capacity of foundation? So the young engineers tend to use only the soil above the footing. They don't use any friction or cohesion contribution from the soil at the failure interface. So is only the soil weight above footing responsible to resist the uplift? This is the first question. So what do you think about it? How do you do it? The second question is, do you incorporate any factor of safety for uplift capacity of shallow foundation? Or do you just use the weight of the chunk of the soil and then compare it with the uplift you are facing in your foundation due to lateral loads? Basically, in case of shades, we get such uplifts for wind loads, right, where bracings are located. Do you think that there are other factors such as cohesion in clay soil or friction in sandy soil which may increase the uplift capacity? You see that when the foundation will be pulled away, there will form some failure surfaces. So in these failure surfaces, there will be some interaction between the two surfaces in either cohesion in case of clay soil or in friction in sandy soil, which may increase the uplift capacity. What do you think about it? Okay, so really the discussion of this on this topic will be based on the chapter 8, uplift capacity of shallow foundations, which is taken from the book of Braja M, Shallow Foundations, Bearing Capacity and Settlement. So I want to go in depth into the geotechnical aspects of the uplift capacity of footings or foundation. However, I will touch the mostly used method, Meyerhoff and Adams, so that the viewer can get some idea how the various geotechnical coefficients work in the formulas. And then we will try out some examples to get better idea. So the methods discussed in the books are the Ballas method, Meyerhoff and Adams, and the one of Basic, and the other one is of Saidi. Mainly, the author encourages the use of Meyerhoff and Adams method. So he gives some reason behind this. So before going to Meyerhoff's method, the most easy method is that of Ballas theory. So this is the general procedure. Okay. What is happening here is that the contribution of soil resting on the footing will come into play, and also the contribution of the soil in friction or in cohesion will also play a great role here at the failure surface. This line you see, the thick black line, this is the failure surface when the footing will be pulled away. So there are some data here. DF is clearly, we can see it from here, that it is the depth of the foundation. It's up to the bottom of the foundation, not the top. So you have to keep it in mind. And since we are dealing with sand, we will have phi value, the angle of friction. and then gamma is the unit weight of sand. So in this formula, you can see that we have df, which is the depth of foundation. The gamma is the unit weight of the sand, which is, say, for example, 17 to 19 kilonewton per meter cube. df is, you will get it from your existing foundation design or the proposed foundation design which you are doing. And then these two items will be multiplied by a summation of functions f1 and f3. So this f1 plus f3, f1 is again a function of this phi and df over b, and f3 is also a function of phi and df over b. So the value of f1 plus f3 is provided in the literature directly. So for example, f1 plus f3, you can get it from this particular chart. So for an example, if your foundation depth is, say, for example, 1.5 meter, your footing width is also 1.5 meter, then you get a df over b equals 1. Say this line then is of particular interest for us. Okay, so you have sandy soil. Say that you have your phi equals 30 degree. So this vertical line intersects this curve at this point. So you will have a value of f1 plus f3 equals close to 2.3 maybe, or 2.28, something like that. So you have this data. Then for this, you have 2.28 or 26, whatever. Then you are done with your calculation. So let's check out an example. Square footing, B equals L, 1.5 meters. Foundation depth is 1.5 meters. Soil unit weight is 18 kilonewton per meter cube. Sand friction angle is 30 degree. Q equals to 138 kilonewton. If you put all the data or chunk together all these data here, you will end up getting this result, 138 kilonewton. Okay. So this is fairly easy. The theory of Meyerhoff and Adams is the mostly used method. Okay. So in this method, the formula for calculating the uplift capacity is given in this form: FQ equals QU over gamma B LDF. QU is the ultimate capacity, ultimate uplift capacity of the foundation. Okay, so you end up getting QU equals FQ multiplied by this denominator, right? So it's easy to do. QU equals FQ multiplied by gamma B LDF. So if you look at the formula, you can see that all these data are known to you. Gamma is the unit weight of the soil. B is the foundation width in case of rectangular foundation. L is the length of the foundation or footing. DF is the depth of the foundation from the existing ground level or the finished ground level, whatever. In case of proposed foundation, you can use the existing foundation depth if you are not sure how much finished ground level will be, at which level finished ground level will be. And in case of existing foundations, you can go with the finished ground level, which is the plinth level of the ground floor. So all this data are known to us. The only data we don't know is the FQ, right? FQ is the dimensionless breakout factor as mentioned by the document. The FQ factor can be determined using this formula. Again, you can see that this formula contains DFB, BL, DFB, KU, 10 phi, and here M. So the only two data we don't know in this formula are M and KU. All the other data are known to us. Okay, so let's see how we can determine the values of M and KU. Then we'll be done. Let's see. Okay, I have given the formula here again. The value of KU can be determined from this graph based on the soil friction angle phi. Say, for example, if you have a phi value of 35 degree, probably you are going to get a KU factor equals 0.94. However, BM Dash says that the variation of the nominal uplift coefficient Ku with the soil friction angle phi is shown here. It falls within a narrow range and may be taken as equal to 0.95 for all values of phi, varying from 30 degrees to about 48 degrees. So he makes it easier for us that for 30 to 48 degrees, we can comfortably consider the value to be 0.95 rather than taking out the data from this graph. Since you can see that the minimum value here is about 0.92 and the maximum value here is about 0.97 or 965. So 0.92 to 0.965 is a very narrow range, and you can take the average. Since the value is already 0.95 or 9293, it will not affect the outcome much. The other factor we need is M. M can be determined from this table 8.1, based on the soil friction angle. Say again, for a soil friction angle of 30 degrees, we will have M value equals 0.15. Phi value is known to us, right? Before we are doing this calculation, we know the phi value from our soils report. Again, in this page, the maximum FQ, which is permissible to use for a particular design, is given here. Say, for example, if soil friction angle is 30 degree, the maximum FQ, which can be practically used for your structure, for your foundation uplift design, is probably this 30 degree intercepts at this location, and it goes here. Probably it is 8, right? It is 8. So whatever value you get from this calculation or from this equation, it cannot exceed this value of, for 30 degree, it is 8. You cannot exceed 8. However, in most cases, you will end up getting 2 or 3 from this equation. Okay, 2, 3, 4, etc. You cannot. The maximum value of this 8 is you can hardly reach it. Okay, so why is this factor given? It's given because when your foundation is well below the existing ground level, then the failure surface will not come up to the ground level. It will end up at some point below the soil level, below the existing ground level. Okay, so it means that since the failure surface has not formed up to the ground surface, the uplift capacity cannot be taken for the full length of the curve. Okay, so up to this point, say for example, if this is a point here, up to this point, you will get the uplift capacity. So this thing is accounted by this maximum FQ permissible. So which theory or method should we use? As mentioned by BM Das, the method of Meyerhoff and Adams is more applicable to a wide range of foundations and provides as good an estimate as any for the ultimate uplift capacity. So this theory is recommended for use. So we can go with this theory. What about factor of safety? In many cases, what young engineers do is they take the weight of the soil here, okay, at some angle also. Some engineers take the weight of the soil just above the footing, right? This area, say for example, A, B, C, D, this soil is considered in the uplift capacity. Sometimes some engineers, they make an angle with this point. Say for example, it is 30 degree with the vertical, 30 degree, right, with the vertical, and then they additionally consider the soil falling in the inclined line I'm proposing here. Say for example at 30 degree. So this all soil is considered. However, they do not use any factor of safety. You can understand that uplift capacity is a geotechnical capacity, right? And in case of the compression bearing capacity, what we do is we use a factor of safety of 2, ranging from 2 to 3, or 2 to 5, right? In case of foundation bearing capacity in compression. Then why not in tension or uplift? The book of Braja M suggests that in most cases of foundation design, it is recommended that a minimum factor of safety of 2 to 2.5 be used to arrive at the allowable ultimate uplift capacity. So you can use 2 for your uplift capacity of your foundation, but it's better than using nothing, right? And you should use at least 2. Otherwise, it will be on a design, and there may be cracks in your soil during uplift, etc. You don't want your soil to be cracked up to the existing ground level, right? There is another thing I have not discussed so far in the slide is the maximum permissible FQ value, the non-dimensional breakout factor, which you can use. Okay, so let's talk about this. Say, for example, when your soil friction angle phi is 35 degree or 30 degree, whatever, I'm taking here 35 degree for this example. For 35 degree, let's say 30 degree, then we get a FQ maximum equals, say, for example, it is 8. It means that what you're getting from this particular formula of FQ, this one, 8.20, which I have shown you in my slide, what you're getting from here, FQ, say, for example, it is 2. Most probably it is 2 to 4 or something like this in our practical cases. It doesn't really go beyond the value what we have seen in the previous graph, which from which we got 8. However, if in some cases this value of FQ goes beyond, say, this value shown in this curve, then we cannot go beyond the value provided here. So we have to remember this. However, there is another catch. This graph is provided only for square and circular foundations. This factor FQ will have to be adjusted for the rectangular foundations. There is a procedure mentioned in the book how to do this. Okay, so how to do this is fairly simple. I will take you through this once more in an example I have done in a spreadsheet. However, I'm trying to introduce you to the formulas here. First of all, df over b CR, if we go back to this formula, FQ is dependent on M, KU, okay, and BL, we know them, and df over b, okay. Now, the graph what we have shown for maximum value of FQ is the FQs there have been determined using the df over b critical, which means that the maximum value of df over b up to which your FQ will be okay. Say, for example, here df equals, say, for example, it is unrealistically, I'm assuming a data, say it is 8 meters, 8 meter. So it's no longer a shallow foundation. However, let's take a data 8 meter, and the footing width is only 1 meter. Say it's a strip foundation or something like that. So df over b, 8 divided by 1 equals 8, right? So for such high data, the failure surface will not actually reach this surface point. It means that the failure surface, the failure line will end somewhere below the existing ground level, say at this point. So this point is called the critical point, okay, up to which this failure surface will work. So you will not get your friction or cohesion contribution up to this, from this point to this point. You will only get the contribution from this point to this point, up to the critical point, okay. So this is what has been considered here. So let us see how we can determine the maximum FQ using this same formula, okay. Here, df over b critical for square foundation has been provided. We are not dealing with circular, we are only dealing with square and rectangular foundation. So for example, for 30 degree, the value of df over bcr will be, say, for example, 4, okay, 4. We have to adjust this value for rectangular foundation. There is another formula provided for rectangular foundation. This CRR means rectangular foundation, critical df over b value. This value can be determined using the value of square foundation, which we have just seen from the previous graph, which we found to be 4, right? The critical depth over width ratio for a square foundation, which is 4, for example, for 30 degree, and then L over B, we know this, we get this value easily. This value cannot be higher than this value. Again, what we got previously is 1.4 for df over b, critical for a square foundation. We multiply the 4 by 1.4, then we get a data. Say, for example, the value of critical depth over b ratio for rectangular foundation will be the minimum of this first portion and second portion. Okay, then we will put this df over b CR into this formula. Okay, to get the maximum permissible FQ, since we have said you already that we have demonstrated to you that the maximum depth over B ratio, which is beneficial, which is actually working to give you the friction capacity, to giving you the benefit in friction, is up to this certain df over B CR. So considering that value, the maximum value can be determined from here. So FQ is calculated twice. Okay, so let me take you to an example so that you can grab the idea better. So I have made a spreadsheet to calculate the uplift capacity of shallow foundation in sand based on the Meyerhof and Adams procedure. So I have width of the foundation, length of the foundation, df, foundation depth, gamma, phi, and factor of safety is 2 here. df over b equals 1 in my example. A equals 4.5 meter squared. So we have already discussed that the formula for calculating the ultimate uplift capacity is this: FQ multiplied by gamma ADF. Gamma ADF is known to us. FQ can be determined from this simple formula. FQ is dependent on M and KU, which have to be determined additionally. M can be determined from this table. For 35 degree here, the M value will be 0.25. For KU, we have already discussed that Braja M does suggested using 0.95 for any value in between any value of solid friction angle from 30 degree to 48 degree. So we can use comfortably 0.95 here. Chunking this data all together into this formula, we end up getting FQ equals 2.16. However, what we need to do is we have to find the critical depth ratio, critical depth to width ratio for our foundation. Okay. In our case, let us first determine the critical depth to width ratio for a square foundation. This one is actually for a square foundation. There is no graph given for rectangular foundation, since it is hard to produce such graph for rectangular foundation for unknown length and width. So at first, the formula given here is for the square foundation. So for 35 degree, we get a value of 5.3 for a square foundation from this graph. Then we go back to the formula which we have discussed before. This specific formula, we can use this and get our rectangular foundation's critical depth to width ratio. This is 6. 5.3 becomes 6. Okay. Then we will put this value, which is 6, into this equation. Then we will get FQ maximum allowed is 12.99. However, since our previously determined FQ value 2.16 is less than 12.99, therefore the lower value governs. Therefore, we have got our FQ. Then we can chunk together all the data here and determine our KU. KU becomes 254 kilonewton, and using a factor of safety of 2, we get allowable uplift capacity for our foundation is 127 kilonewton or 28.56 kips for this foundation. I think this video has been helpful for you. Let me know if it was helpful to you. Okay, bye. Allah Hafiz.